Welcome friends. In my last videos we have discussed about the axial forces, shear forces, bending moment and the relation between the axial force, shear force and the bending moment. These few of the topics we have discussed in my previous videos. So let us start with the new topic, that is twisting couple today. The twisting of a structural member about its longitudinal axis by two equal and opposite torques is expressed through a certain angle. So for that, let us draw a twisting member, a cylindrical rod we can consider. So let me draw this on the board. So let us consider a cylindrical rod here of length L. The length of the rod is L and the radius of this rod is R, with its upper end fixed. This particular end of the rod we have considered as fixed and it is not fixed. So let a twisting couple be applied to the lower end of the rod in the in a plane perpendicular to its length. So this plane we are considering, in this plane we are applying the twisting couple to twist this rod in this direction. So let the rod twist through an angle theta. We will consider this angle theta, which is the angle of twist. While the rod is twisted, the restoring couple acts in the opposite direction. We will twist the rod in this direction, so the restoring couple will act in the opposite direction, and in the position of equilibrium the twisting couple is equal and opposite to the restoring couple. If this is our twist, so the restoring couple is in the opposite direction. So in the equilibrium position of this beam, so what will be, these will be equal. So to calculate this couple, let us consider the solid cylinder to be made up of a large number of concentric thin walled cylinders, we can say. This particular end we are considering, so this is made up of a large number of the concentric thin walled cylinders. So let us consider one such hollow cylinder of radius x. So let me draw that particular diagram, that figure. These are the concentric circles. If here is our point O and this is the X, and we have this particular point B and B dash. So what exactly this will be, we may consider it here, it's B and it's B dash. And for this a small part we are discussing, that is dx, if we will represent it by dx, and the radius of this is r, so this is represented by r. Okay, so now now the rod is twisted through an angle theta. So this is an angle theta. Here we may consider it is twisted through an angle theta, and the angle through which the rim of the cylinder is sheared, that is phi. Here you may consider this particular angle by which the rim of the cylinder is sheared, that is phi. So here now in this diagram of the rod, here we can see in this structure, so this particular value of b dash can be found as b b dash, that is equals to if L is the length, this is the length of this, in this triangle also we may consider b dash, and in this portion also we may consider. So this is arc, actually it is not a exact triangular form. So we are just trying to find out the value of this b dash by this structure and by this structure. So the upper, for this upper structure, it can be as this into the angle. B dash is equals to this, and this is what, this is the length. So length into angle, this, so we may write it as it is L phi. And similarly for this portion, also we can say this b dash is equals what is this, this is actually x. Here we may consider this is x. So the this b dash is what it is here, x into, again b dash can be written as x theta. Okay, so by these two equations we may have the, by equating these values we may write as L phi is equals x theta, or we can say phi is equals to theta by Lx. So we may write it as equation number 1, and we can say that the phi varies with x. That is, the shearing stress is not uniform throughout the material. Okay, so we can say the shearing stress is not uniform throughout the material. So if n is the rigidity modulus, so let me erase this part now, so to discuss to write it or in the next portion. So we can say as if n, we will represent the rigidity modulus. So that can be n is equals shearing stress upon angle of shear. Okay, so by this we can say, so what exactly the shearing stress is. Shearing stress, that is equals to, now what is the angle of shear, that we may say, we can say that is phi. Okay, so this we can also represent by f also. So here we can say that the shearing stress, that is equals to n phi. Either it can be written as by substituting the value of phi from equation number 1. So you can have the shearing stress, that is equals to n x theta upon L. So this is our equation number 2. Now the face area of the hollow cylinder. So what was that hollow cylinder, the face area of that, we can say here, if this type of the hollow cylinder we have considered. So the face area so that can be written as what is it is 2 pi x. X is here we have considered as the radius of that inner circle, so that into the distance, that is dx. So this is the face area. So the total shearing force on this area is equals to this multiplied by this the area multiplied by the stress. So that is our shearing force. Shearing stress is what, that is shearing force upon area. Okay, so we can say the shearing force on this particular area, on that area, so we can write is 2 pi x dx into this particular term we can write here. So it is n x theta over L. Either we can write as, this can be as it is 2 pi n upon L theta, this term, and x we can write as into x square dx. So this is our equation number 3rd. So therefore the moment of the force about the axis o dash, that particular vertical axis we have considered, o dash we have considered na, like this is o and this is o dash. So L was the length, and here that distance is x. So the moment of this force about this axis, so the distance is x. So we can write the moment of the force. Therefore about the axis o dash, so that can be this multiplied by the distance. So what is the term here? It is 2 pi n upon L theta x square dx, again multiplied by the distance, that is x. So we can write it as it is 2 pi n theta x cube dx upon L. So this is our equation number 4. So the total twisting couple of the cylinder can be obtained by integrating this expression between the limits 0 to r. Okay, at the center the distance, the radius at the center it is 0, and at the maximum point, that is our radius. So we may integrate this from 0 to r to calculate the couple, twisting couple. So the total twisting couple on the cylinder, okay, that is equals to integration from 0 to r of which term? This term. So if we will integrate this, we will find out the total twisting couple. So the values are, it is 2 pi n theta upon L x cube dx. So we are integrating with respect to x, so that is why this term may be written as it is 2 pi n theta over L, integration of this term only from 0 to r x3 dx. Okay, so what will be the integration of this term? That is simply x4 upon 4. Okay, so I'll write it here. I can write on the top. On the top we can write it as let me raise this part also. Okay, so what will be the value now from this equation? It is equals to simply this term is same, it is 2 pi n theta over L, and after integration we will get x4 upon 4 from 0 to r. Okay, this is the condition, and if we will put the limits, then the resultant of this twisting couple on the cylinder can be written as, it is simply, this is r4 and 0 will be cancelled out, so 2 is also it will be cancelled. So by simplifying this term, you will get it is pi n theta upon L, it's 2L, 2 will be cancelled out, and it is 2 divided by 4, that is 2. So simply here we will write as it is, in place of x it will be now r4. So this is our equation number 7. So if theta is equals 1 radian, it is 1 radian. Okay, then we have, so let me raise this part also. Okay, and finally we can have the value of this twisting couple. Per unit twist. Okay, because we have put the value of theta 1, so that is why C is equals pi n r4 upon 2l. So this is our equation number 8. Okay, so this twisting couple per unit twist of the wire is also called the torsional rigidity or the modulus of torsion, this particular term. Okay, of the cylinder. For the cylinder, this may be considered as the twisting or modulus of torsion or the torsional rigidity. Okay, for the hollow cylinder, if we will consider, we have considered as from 0 to x. Okay, if this was our circle, from 0 to x we have, for the concentric circles we have considered. So if it is an hollow cylinder, so this, if this radius is r1 and the outer radius is r2, so then we need to integrate this particular term that in our previous equation we have integrated where from 0 to r. So now we need to integrate from this r1 to r2. So I am just putting the values directly, what will be the result for that. So in that case, for the hollow cylinder, so the twisting couple C, that is equals to from r1 to r2 2 pi n theta upon l x cube dx. We have integrated in our previous section also. Here we have the value of that integration part. So directly I am putting the value as simply it is r4 minus 0 we have considered. So here it is r2 minus r1. So finally on solving, we will have the twisting couple per unit twist, that is C is equals pi n over 2l, that is r2 4 minus r1 4. So this will be the equation for that value. If this is our equation number 9, then it is 10. Okay, so I think it is very much clear to you. Okay, in to understand for more topics in the physics, so you please watch my videos for the upcoming videos and subscribe the channel also. Thank you, thanks for watching.